Good morning, one and all. Myself, Sankararao, a PhD scholar working in the Department of Electrical Engineering, IIT Hyderabad. So my paper title is Store Nitrogen Estimation in Groundnut using Hyperspectral UAV Imagery and Machine Learning Techniques. So the motivation for this is like livestock animals are like very important part of the agriculture, especially in livestock mixed farming systems. And however, due to like urbanization and land utilization changes, the grazing lands has been gradually decreasing. And recent studies show that around 50 to 70% of the livestock food supply comes from the like store, like leftover harms, like crop residue kind of thing. So for that purpose in agriculture, especially in addition to improving the grain yield, the crop improvement programs are working to improve the crop residue quality and quantity also. For that, phenotypic scientists are working to enhance the developing better crop varieties, not only produce more grain yield, but also to produce better quality crop residue also in terms of store nitrogen or store digestive organic matter and all. However, the problem here is assessing many genotype varieties in the real field conditions. So for that purpose, actually they mostly rely on the traditional phenotyping methodologies like laboratory measurements or else like field measurements and all. If they want to estimate the store quantity and all, they have to manually measure in the fields or else store digestive organic matter. They have to do some laboratory assessment and all. This is very labor intensive and time taking and also costly also. This delays the phenotyping studies and all. So one of the potential solution is the drone based imaging techniques. Especially drones have large coverages, high temporal resolutions, and also more spectral and spatial resolutions and all. So motivated by this, we are using hyperspectral imaging camera mounted with a drone in 400 to 1000 nanometer range for store nitrogen estimation in groundnut crop. We can use multispectral as well as RGB, but the quality estimation in terms of store nitrogen is more accurate if you use a hyperspectral camera, which provides rich spectral information. With that purpose, we have used this. So, and also here hyperspectral cameras produce more information. So, and in real phenotypic studies and all, we have very less ground truth data, data samples. So to reduce the dimensionality and to improve the accuracy, we were relying on future selection techniques in this study. So this is the system that we are using. We are using a PICA-L hyperspectral imaging camera, which acquires data in 400 to 1000 nanometer range in 282 spectral bands, in very narrow 2.1 nanometer spectral width. This is mounted on a UAV, a DJI UAV, and other equipment we have used to collect proper data like INS system as well as gimbal and downwelling irradiance sensor for radiance calibration, reflectance calibration we have used. And we collaborated with ICRIS at Hyderabad, where the crop physiology scientists for conducting these experiments. So this is the groundnut experiment that was conducted post-rainy season in 2021. And it is having two treatments, well-watered and water-stressed treatments. So each treatment is having 8 genotype varieties with 2 replications. So total we have 32 plots. Here, for water-stressed plants, the irrigation was withheld after 30 days after sowing. And in between, life-saving irrigation was given, but standard required nitrogen was given for both of them. But here the nitrogen like content of the store changes because of like nitrogen use efficiency of the different genotypes as well as water stress due to that. And ground truth measurements, this was done by ICRSAT. So they have harvested plants, 8 plants from each plot. Actually, the plots are 8x3 meter plots. So that was like oven driven and 60 degrees temperature. And then it was the nitrogen measurements were made in correlation with NIR measurements. So this is the statistics of the ground truth data. So we have around at 2 different growth stages, vegetative and grain filling stage, we have collected data. We have 64 samples. So this is the flow that we have followed for analysis. First, we have done data calibration like reflectance calibration, like to get absolute reflectance of the data. We have used the data of downwelling gradient sensor for this correction. And then we did geo-rectification. Actually, the camera we are using is a push-broom sensor. So there were like due to instability of the drone, sometimes there were some kind of distortions were there. To correct that one, we have used INS data to correct that. Then after that, actually we observed that especially in our camera, what we are using, about 890 nanometer, there is some noise, especially AWGN noise is there. To correct that one, we have used different like denoising techniques, state-of-the-art techniques. From that, we have used fast hyperspectral denoising technique to correct the data. And here we have like each 8x3 meter plot, we like one measurement is there, that is the ground truth. So for that purpose, we have only considered the canopy pixels of the groundnut, and we have taken the mean spectrum that we treated as X and the laboratory measurement treated as Y. Then followed by we have used feature selection. We have from scikit-learn library, we have used like explored different feature selection techniques like minimum redundancy, maximum relevance, and select from model and recursive feature elimination. These things we have explored. And followed by once we have got the relevant features, top features, then we have used some machine learning regression methods to estimate the nitrogen. And these are the performance metrics that we have used: mean absolute error, coefficient of determination, mean square error, and mean absolute percentage error. And here to split into train data into 64 samples into train and test samples, we have like used Kennard Stone cross-validation technique. We have used a 3-fold cross-validation. And these are the, you can see in the table, these are the estimation results on the 64. Mean and standard deviation we have presented. And we have used different, as I was telling, different feature ranking techniques. So actually, we have ranked the features, and then for each feature, we are trying to estimate, like from using the top ranked feature, 1 feature, 2 feature, like that. We are trying to check like how well it is estimating the nitrogen. So based on that, we found that 12 are good enough, 12 features. And using those 12 features, we estimated with around 82.9% R square and 3.82% mean absolute percentage error. So, so this is the the summary of the work. So we have explored the potential of UAV hyperspectral imagery for store nitrogen estimation in groundnut. And the future scope is here, like if you observe here, here we tabulated the top features ranked by the different feature selection methods. The problem here is each method is like scoring differently, the relevance of wavelength scoring differently based on the technique that the selection method is using. The thing is, we have worked on like ensemble learning, where we can combine the advantages of the different feature selection methods to come up with better wavelengths or wave bands, which can better estimate the nitrogen content. And another thing is the future scope is we are working on actually Here we have taken the mean spectrum where we can say we have ignored the spatial information present in the data, only we have used the spectral information only because of limited data samples. Actually, deep learning techniques all require like CNNs, V8s require more label data. So for that purpose, we are exploring self-supervised learning techniques. So for representation learning, we have like large volumes of unlabeled data of different crop varieties. From that, we are trying to learn the better representations. Using those representations, we are better able to better estimate the nitrogen content. This work is currently going on. So that's all. Thank you. Thank you.